Range of AI solutions, from cloud-based deployments to hybrid quantum machine learning models. He has given workshops and mentored others in emerging technologies, contributing to research papers and developing proofs of concept across industries. Passionate about education and innovation, Antonio has taught at universities and schools in Mexico and has participated in international hackathons in Paris, focusing on AI agents and startup development, sharpening his skills in real-world, high-impact environments. I give the floor to Antonio Contreras.
For a small division that we're creating for researching on different areas, for doing collaboration with different people. So if anyone is interested in collaborating in any project that wants and maybe evolve to a product in the future, it's open. Just quick announcement. So let's continue with the presentation. So we'll talk about resource efficient CNNs and TIG welding defect in using data balance techniques. So this is the outline that we will follow: production methodology, experimentation, conclusion. So let's talk first of all about the problem statement. Basically, traditional methods for detecting welding defects have been not so efficient, sometimes even more costly. So the idea is first of all to create a model that can detect welding defects in the production environments and help to first of all reduce the scrap produced by the machines that are actually automated, and also if it's possible, remove it for 100% or at least just detect it. So that's basically it. For now, there's different data sets available for these techniques and companies that are also interested in this. Yep, that's pretty much it. So for that, we selected two datasets who are available publicly, and you also can take it. These datasets were produced by Fraunhofer, which is a company in Germany. And basically, it's two datasets, both focus on welding defects. Here we have the classes. The first of all, it's called corresponds to a dataset called Aluminum 5083 TIG, which TIG stands for a machine which is used in welding. Also, we have another dataset which is stainless steel 304 TIG, which also it's from the same company. Basically, as you can see here, we have the different use cases. We have the good weld, which is this one, the first one. Let me point out this one. We have burn through. Basically, the welding machine burn the plate, so it is burned through. We have contamination from different things on the materials. We have also lack of fusion, misalignment, and lack of fermentation. And also, just to a quick notice, in the other dataset, we have also lack of shielding gas and high travel speeds, which is other conditions that were not available in the other dataset. So basically, these are all the problems that can arise when doing welding, at least the automatic machines that are being used now. So just a curious thing, someone asked me, why don't you make the machines better? That's also an interesting question, because it's true, maybe we can make the machines better so we can avoid these problems. But someone explained to me that the main problem is that the operators are the ones who set up the machine. So if they make an error, the machine will do an error. So that's basically it. Even if we make better machines, we'll still have these problems. Maybe you can implement an algorithm which detects the material that you will use and automatically gets the order or something and set it up automatically. That could be also a good solution for this part, but at least we're focusing on inspection for now. So a little bit of the state of the art, as I just mentioned, the first dataset was developed in 2019 by the company I already mentioned, Fraunhofer. And basically, they created a dataset using a HDR camera, and they tried to solve the problem with neural networks. At first, in this paper, they produced some models that were not as good as the ones that we will present now. Most of them got around 60% on accuracy, F1, recall, and precision. So the models were not so good. But one thing to mention is that they didn't use architectures or pre-trained models. They created his models from ground. So that might be why they didn't get so good results. They also generated the other dataset and did almost the same experiments, creating his own architectures to try to solve their problem. Then they tried to use transfer learning, which also led to a little bit of better results. They got around 80 in the binary problem, and in the multi-class classification problem, they got around, I think, 70%, which is also very good, but it's not the thing that we want. We can probably having 99 if we can. So Then other people try to use different approaches using pure machine learning and also using neural networks, some sort of hybrid combination. And also a team from China tried to develop models that were not only having good results, they also got pretty good results. They got results, I think, around 90 to 95. And also the models were very fast. So this is the approach that they follow to creating architectures that were small and also that could have great results. And basically, we also produce a solution trying to use transformers, which also led to a very good results. But the main problem was this was not as cost efficient or as fast to run in a GPU. And just imagine if you have to invest 1 GPU per machine, that would be very costly. So we don't want that. We want to have maybe a model that can be run, if possible, on CPU. But as you know, images are very highly complex to process. So this might not be as fast or as easy that it might sound. And now our work, which is trying to find architectures that are small and resource efficient. So we can maybe use it on GPUs if possible, if not, but we can go farther and try to use something like Raspberry Pi. This is something for the future, just to know. So for this evaluation, what we did is we found different models. We tried to find models that were small enough. I think this one over here is around 1 million parameters. I think 3 million parameters, something around that, which is pretty big, as we can say, but not as big as, for example, a model like an LLM, which has 80 billion parameters, 100, I don't know, whatever parameters. So basically, this is the first model that we select. We selected because a lot of people were reporting that they were having edge devices running these models, and also were very efficient. We also select Redjet Y, which this one was a little bit more bigger model. It has around 8,000 million parameters. This was not as small, but it's supposed to also be relatively efficient in resource constraint problems. For this also, we focus on using transfer learning. We didn't train the models from ground. We tried to have a version that was already trained by someone else and then take that model and use it for us. And basically, the design philosophy from these architectures, the thing that we were trying to find is someone who tries to have good accuracy, but also have a very fast model that could do inference very fast. So it can be used in a production line, for example. That could be the thing. So let's go very fast with the pipeline that we follow for training this model, with these models. First of all, we use both datasets, as you can see here, the ones that I present, the TIG aluminum one and the stainless steel. And for these both datasets, we use these approaches for training the models. Basically, the first one, which is over here, undersampling, what we did is that we reduced the amount of images per class. So we maintain a balance between different classes, just having a smaller amount. That was the first thing. We also tried to use class balance loss, trying to use in the cost function some sort of extra thing that will help us to address if there's some imbalance between the classes. So we took all the data set as it was and put it there, added to the cost function, and run the experiments. And this one, which is weight random sampler, which basically it's an algorithm that will address these things of the balance while running the batches for us. So that's basically it. And here are the experiment configurations, the same that I mentioned. We take the first data set, we apply these 3. We take this data set, we apply the same 3 for both models. So we use both classifiers. So at the end, we have 6 experiments. Okay. Also, I forgot to mention, we didn't tackle the binary class classification problem because it was not as hard, we would say, as a multi-class problem. So we will focus only on the multi-class problem. Here we have the dataset experimentation. As you can see, this is the original dataset, and also his divisions. For example, we have the first one, which is the undersampling. We try to manage that every single class, which are 6 that we mentioned at the start, has around 6,000 image and 10,000 for validation and 6,000 also for testing. We also have the other 2 experiments, which, as you can see, have 15,000 images. It's a lot of images. But basically this didn't use the undersampling that we mentioned. It's just used the dataset directly. It's almost the same thing we got from stainless steel, only the main problem was that the class that has the least amount of images has only around 200 images. So we have to reduce too much the dataset so we can address this thing. So that's why we have around 1,000 images only on the stainless steel. For the validation, we got more images, and same thing for the testing. So as you can see here is that, just to mention, I think this wasn't presenting on the diagram. This was bad from our part. But this, for example, these 1,000 images are created when training the model. So it's random. If you try to run it again, you will get another random sample of 1,000 images, which are balanced and have the different classes. So, and here we have the results from each experiment. One of the things that we have to mention is, as you can see in this one from the ShuffleNet experiment 1, run 1. As I mentioned, we did various runs to this comparison. But as you can see, when we do the undersampling on the first one, we get not so good results. It's getting very, very bad results. This is we get not so good results. We are around the same thing how we mentioned at first, not getting good things. But as you can see, we run different experiments, and also we have the time of prediction per image. I think for this ones would be better to have the frames per second, but I think that we didn't include in that part. But that's basically it for this section. So let's go with the second dataset. In this one, this was a little bit weird. We got better results. To be honest, we got less data, but it seems that maybe there was something wrong with the pipeline, because we got around 98 in this version, which is, it's supposed to be the same, but the difference is we use the other dataset, which has less data. There was something that we noticed. We tried to run the experiments again, I remember, but it didn't change. I think we didn't do anything wrong. We just had bad luck, I suppose. But at least running the experiments, that was the thing that we noticed. And as you can see, the best model that we have is this one called RegNet, which got around 98. And yeah, but to be honest, the fastest one is still being the ShuffleNet, because this is obviously something that is, we would say, obvious, because it has less parameters and can be run faster in a GPU. So that's basically this part. Okay, so now our classifier would say ShuffleNet want to outperform several previous models. And as you can see here, we have different approaches for the papers that we mentioned at first. For example, this one was one of the experiments that we did, which is the bait vision transformer. We got around 98. This model got very good results, but the main problem was what's super slow. For example, processing an image, it would take like 1 second, 1.5 seconds. That's too much for maybe an inspection line. That's not feasible. And so obviously also this model was very big, so it will be hard to load it in a GPU, or will be so cost to load it in a GPU and run it in the machine power by power. So yeah, that's why we get in this other direction. We also have the one from the Chinese team that got around 89 of accuracy. Why didn't we put the other metrics from the other, like F1 precision recall? In the papers that they did, they didn't include it. So that's why we just compare the accuracy between our models and their models. We also have the original paper comparison. As you can see, they created an architecture of convolutional. They got around 70 on the multi-classification problem. And they got, in a fully connected neural network, just dense neural network, they got around 46 in the multi-classification problem, which is not so good in comparison to at least the one that we developed with bait, and also with the one that we developed with ShuffleNet that got very good results. And also it's very fast. Also we can compare the RegNet, this part. RegNet, as you can see, also we got very good results in comparison to other models in the same category. And yeah, as you can see, this is for the stainless steel dataset. I forgot this part. Let me go with this section. And in conclusion, we can see that most models are getting good results if we do undersampling techniques, if we maintain this approach. Also, if we have pre-training before. Also, we noticed that lightweight models are continue to having good results, but we need to do a little bit more investigation to try to find even smaller models. Just imagine if we, for example, could run a model like whatever neural network that has around 80% of accuracy in a just Raspberry Pi Pico, just to give you an example. Because a Raspberry Pi Pico costs like it's around $4. And just imagine putting an embedding device on a pipeline that costs just $4. This could be a very efficient product, and also a very good model that it's so small that can be run on these kind of devices. And yeah, for future work, this is more like I would say like a brainstorm. This is not something that we will do directly because I mentioned this is going to different directions. But one of the things is analyzing the consistency of the annotation, because also one of the things that we found out when running the experiments is that the annotations of some of the dataset were not correct. So for example, we found something which was burned through, but in reality was lack of fusion. We compared the images and we did the experiment. So that's one of the things that we can check. And this was in the first dataset. In the second dataset, most of the images were correctly labeled. But for example, in the first one, we found, I think that we checked manually, we found around 100, but we don't know if there's more. That's one of the things that we have to address. We also could try hybrid approaches with CNN and BIT architectures that are also small. Try to apply maybe neural architecture search or hyperparameter optimization for the same structures, and going to the edge device deployment that I just explained, that for example would be very valuable to have a model that can be run in a Raspberry Pi or in a very small device that it's energy efficient and cost efficient. And this one, they explored the hybrid quantum neural networks. There was some sort of continuation of this. This was not getting good results, but it was going in that direction too. So yeah, this is the reference. If you have any questions, we have 3 minutes. So thank you for your attention.